Hello, Precalculus students. We begin this lesson by discussing angles. An angle is a collection of two line segments that share a common endpoint. So right here is an example of an angle. We have two line segments sharing a common endpoint. And it does not matter whether these line segments are the same length or not. In fact, they could even be rays, meaning perhaps they extend forever in one direction. Now the angle is in standard position if the common endpoint is at the origin of the xy plane and one segment is on the positive x-axis. So I'm going to rotate this angle into this position and overlay this with an xy axis where the origin is at the common endpoint. When you position an angle in this way, where one of the line segments is on the positive x-axis, then we say that this angle is in standard position. The measure of an angle is a measurement of its openness. So here we have an angle that has a small amount of openness, and now we have increased the openness and increased the openness even more. One way to measure openness is to use a unit of measurement called a degree. If a circle is partitioned into 360 congruent wedges, each wedge forms an angle that has a measure of 1 degree. So if you take a circle and cut it up like a pie into 360 equal slices. I've drawn 4 slices, but these are not to scale because we would need to fit 360 of them around the entire circle. But if you focus on just one of them, these two line segments form an angle whose openness is said to have a measurement of 1 degree. So this circle is illustrating the 360 degrees it would take to rotate entirely around a circle. Now when in standard position, consider angle 0 to be off here to the right, and then we imagine the angle growing in a counterclockwise direction. This 30 degrees is referring to an angle that's in standard position. So the two line segments that are forming the angle are this one and this one. And sometimes we'll draw a little arc and put a 30 degrees next to it. So this 45 degrees is referring to the angle formed by this line segment and this line segment. So connecting those two pink line segments forms a 45 degree angle. And this 60 degree angle is the angle formed by this line segment and this line segment, etc. So as we rotate around the entire circle counterclockwise, 360 degrees takes us back to the same position as angle 0. If you take 360 degrees and divide it into 4 equal pieces, you get 90 degrees each. So a quarter of the way around the circle would be 90 degrees. Another 90 degrees would take us to 180. Another 90 degrees would take us to 270. And then the final 90 degrees, which takes us to 360 degrees, which is a complete rotation around the circle. If you cut 90 degrees in half, you get 45 degrees, and there would be 8 such rotations. 45 degree rotation, a second 45 degree rotation, a third, a fourth, a fifth, a sixth, a seventh, and an eighth. 60 degrees is 1/6 of 360. So if we rotate 60 degrees, and then another 60 degrees, and then a third 60 degrees, that'll get us halfway around the circle. And then 60 degrees more, 60 degrees more, and then a final 60 degrees to go all the way around the circle. And 30 degree rotations, we would need 1, 2, 3 of them do a quarter of the circle. So we need 4 times 3, or 12 such rotations to go all the way around the circle. There's 6 30 degree rotations, 9, and a total of 12 30 degree rotations to go around the circle. You will want to become familiar with this circle and all of these angle measurements. Now every angle can be measured in 2 ways, as shown below. So we have an angle that's in standard position. So beginning with the horizontal segment and opening counterclockwise, we can measure the openness, but then beginning with the non-horizontal segment, we can also go counterclockwise and measure this openness. A lot of people will default to the smaller of the 2 options when they say what is the measure of the angle, but in reality every angle has 2 ways to be measured. So if this green angle was 60 degrees, then the orange angle would have to be 360 degrees minus 60 degrees, or an extra 300 degrees, to account for the entire rotation around the circle. Very often we use Greek letters to represent the measures of angles. For example, we may say that the 60 degrees is alpha, and this 300 degrees we may say is beta. And we can see that in this case, the 2 different measurements, if added together, should add to the total 360 degrees, if alpha and beta are the 2 different measurements of an angle. An acute angle is an angle whose measurement is between 0 degrees and 90 degrees, and an obtuse angle is between 90 degrees and 180 degrees. A right angle is formed when the line segments are perpendicular. And as we saw from the circle above, that would be a quarter of a rotation around the entire circle, so it would be 90-degree rotation. When you have a right angle, it is often the case that we put a square in this corner to indicate that we have a 90-degree measurement. Complementary angles together form a right angle. So I put two angles sharing a common line segment. There's one angle, there's the other angle, and they share this line segment. If this measurement is 60 degrees, then the complementary angle would have to have a measurement of 30 degrees, so that together they form the 90-degree right angle. So again, if I use Greek letters, alpha, and this time I'll use theta, to represent complementary angles, then we know that when added together, they should combine to make a 90-degree angle. Supplementary angles together form a straight edge. So the common vertex is right here. Here's one angle, here's a second angle, and they share this common line segment. So if this first angle is 60 degrees, let's call this alpha again, then the supplementary angle would need to have a measurement that would effectively take us halfway around a circle, which is 180 degrees. We've already done 60 degrees with the green angle, and so the remaining number of degrees would be 120 degrees. Let's call this one beta. And two supplementary angles must add to halfway around the circle, which is 180 degrees, thus forming this straight edge. Now, two complementary angles that are non-zero must both be acute. So you have two non-zero angles that add to 90 degrees, which means that both of them must be less than 90 degrees, and that's the definition of an acute angle. Two supplementary angles, it is possible that they are both right, 90 degrees and 90 degrees, but if one of them is acute, like this case here, then the other one must be obtuse. There is a second way to measure angles using a unit known as a radian instead of degrees. 1 radian is the measure of an angle that is formed by subtending one radius length along the perimeter of a circle. So let me begin by drawing the center and the radius. Now if you take this radius as if it was made of string and you begin to wrap it around the perimeter of the circle, you would expect to get about this far, judging by the naked eye, and then we've put our second line segment to form the angle. So this horizontal line segment we'll say has length r, and then this circular arc has length r as well. And this angle is said to be 1 radian. Or you can say 1 rad, or in the case of radians, if you just say 1 in the context of measuring an angle and do not put a unit, we will default to radians. If you mean degrees, you will need to put the degree symbol. If you were to repeat this idea but with the diameter, and try to wrap the diameter around the circle, you get approximately this far. A second diameter would take you roughly here. A third diameter would get you almost completely around the circle, but then you would have this little bit left. It turns out that the number of diameters it takes to wrap around an entire circle is exactly pi diameters, where pi is approximately 3.14. In reality, the digits of pi continue forever without a pattern, but for practical purposes, we tend to round pi to about 3.14. So if you were to ask how many radii would it take to wrap around the circle, well, we would just have to double this number, because the radius twice is the diameter. So note that 2 pi radians corresponds to 360 degrees, because 2 pi radius lengths is what it takes to wrap around the entire circle. Convert each of the angles below to radians. It turns out that 1 radian is a little bit less than 60 degrees. To the naked eye, it might be tempting to say that 60 degrees and 1 radian are the same, but they are not. I know that pi radians will wrap around half the circle. So if I put pi next to this 180 degrees, that's telling us that pi radians as an angle measure is equal to 180 degrees. And if you want, you could put the rad after the pi, or you can just leave the units off, because the default unit is radian, which means that 90 degrees, which is half of 180, this would be pi halves. And 270 degrees would be 3 pi halves. 360 degrees would be 2 pi. 0 degrees, of course, would be 0 radians. Now, if you take 90 degrees and cut it in half, you get 45 degrees. So cut pi halves radians in half, and you get pi fourths. So every time you rotate counterclockwise 1/8 of the way around the circle, you are rotating pi fourths radians. So here's pi fourths, here's a second pi fourths that gives us pi halves, and then here's a third pi fourths. So we get 3 pi fourths is the same measurement in radians as 135 degrees. And then we have 4 pi fourths, which is pi. Rotate pi fourths one more time. We have 5 pi fourths. Rotate pi fourths again, we get that 3 pi halves. Because 5 pi fourths plus pi fourths is 6 pi fourths, which is 3 pi halves. Rotate another pi fourths, that takes us to 7 pi fourths. And then the final rotation, add pi fourths to 7 pi fourths, we get 8 pi fourths, which is 2 pi. Take 90 degrees and divide it by 3, we get 30 degrees. So pi halves divided by 3 is pi halves times a third, which is pi 6. So 30 degrees is pi 6 radians. And every time we rotate 30 degrees, we are rotating pi 6. So here's our first pi 6. Here's the second pi 6. So 2 pi 6 is 60 degrees, but that just simplifies to pi thirds. Another pi 6th rotation will take us to 3 pi 6ths, which is pi halves, confirmed by this. Another pi 6th rotation will take us to 4 pi 6ths, which we can simplify to 2 pi thirds. Another 30 degrees will take us through that middle line and take us to 5 pi 6ths. 30 more degrees will take us to 6 pi 6ths, which is just pi. 30 more degrees will take us to 7 pi 6ths. 30 more degrees will take us to 8 pi 6ths, which is just 4 pi thirds. Another 30 degrees will take us to 9 pi 6ths, which is the same thing as this 3 pi halves. Another 30 degrees will take us to 10 pi 6ths, which we can simplify to 5 pi thirds. 30 more degrees will take us to 11 pi 6ths. And then finally, the last 30 degrees will take us to 12 pi 6ths, which is just 2 pi. Now you will want to become comfortable with all of these measurements in radians, as well as their degree measurement counterparts. Convert each degree measurement to radians. We begin with 15 degrees. Now we saw in the previous slide that 30 degrees was the same thing as pi 6 radians. So if I want to go to 15 degrees, I just have to divide both of these measurements by 2. Therefore, 15 degrees is simply equal to pi 12ths radians. This was a convenient approach because 15 degrees was half of 30 degrees, and I already knew what 30 degrees was in radian measurements. However, we can devise a more general conversion formula to go from degrees to radians. And that process is as follows. If we know the number of degrees, and we multiply it by a conversion factor, where we know that pi radians is the same thing as 180 degrees, then the units of degrees will cancel, leaving a unit of radian. So this conversion takes us to 15 times pi over 180 radians. And then 15 divides into 180 12 times. So this fraction simplifies to pi 12ths radians. We can use this conversion process for the remaining entries of this table. So 140 degrees, multiply that by pi radians corresponds to 180 degrees, and we wind up getting 140 divided by 180 times pi radians. And then simplify 140 over 180, that's 14 over 18, which is 7/9. Generalizing this process, 221 degrees will become 221 over 180 pi radians. But this fraction does not simplify further, so we can stop here. And in general, if you know alpha degrees and you want to convert that to radians, then you simply do alpha divided by 180, multiply by pi, and that's how many radians alpha degrees corresponds to. Now for the other way around, if I know the radian measure and I want to convert to degrees, let's first figure out what 1 radian is. And I'll begin with a similar conversion process. Begin with 1 radian and multiply it by a conversion factor, which is the reciprocal of this conversion factor. So I want the units of radians to cancel, so I need to put radians in the denominator. So put pi radians in the denominator and put the 180 degrees in the numerator. This way we'll get cancellation of radians and keep the unit of degrees. So we get 180 divided by pi degrees. Reaching for a calculator, that's about 57.3 degrees. So it's a little bit less than 60 degrees as mentioned earlier. So every time you wrap one radius length around a circle, it subtends an angle that measures 57.3 degrees approximately. If you have 4.5 radians, that's like wrapping 4.5 radii around a circle and measuring the subtended angle. So take 4.5 radians and multiply it by the conversion factor of 180 degrees over pi radians. 180 times 4.5 is 810. Divide this by pi, and this would be how many degrees? And reaching for the calculator, it's about 257.8 degrees. Continuing this, pi fifths radians. I'm going to leave the unit of radian off, so I'll just say pi fifths times 180 degrees divided by pi. Again, leave off the rad, they will cancel. Notice the pi's also cancel, so we get 180 degrees divided by 5, which is 36 degrees. This calculation makes sense because if pi is 180 degrees, then pi fifths will be 1/5 of 180 degrees. And then in general, if you have beta as your measurement in radians, then you multiply beta by 180 degrees over pi. I'm leaving off the rads. So we get 180 beta over pi degrees. You can use these conversion factors here and here as appropriate to do your conversions from degrees to radians or from radians to degrees. Now let's do some review of how to find the total area of a complete circle and then come up with a way to find the area of a circular wedge, a portion of a circle. So you need to identify the radius of the circle, so find its center, and identify a radius length, call it r. If we know the radius of a circle, then the area, we'll use capital A, is pi times the square of the radius. Now what if you need to find the area of just a circular wedge? So you can see these two dotted line segments, they form an angle that share the center of the circle. Let's say we know the measurement of this angle is alpha degrees. Then we just need to figure out what percentage of the entire circle is alpha degrees. And we know that the entire circle is 360 degrees. So imagine alpha was 30 degrees, for example. 30 degrees divided by the total 360 degrees gives us 1/12. That's unitless. This is telling us that 30 degrees is 1/12 of 360 degrees. So it would make sense that the area of this circular wedge should be 1/12 of the area of the entire circle. This gives me the means to come up with the following formula. Area of this wedge will be found by doing alpha degrees divided by 360 degrees to figure out what fraction of the circle we're looking at, times the area of the entire circle. Suppose we know the measurement of this angle, but in radians, beta radians. Then we do something similar. We know that the entire circle is 2 pi radians. So to find the area of the wedge, we would say beta radians divided by 2 pi radians gives me what fraction of the entire circle we're looking at, and then multiply that by pi r squared. Now in this case, we could simplify a little bit further. You'll notice the pi's cancel, and so we just get beta halves times radius squared. So we'll use either one of these formulas depending on whether the angle is measured in degrees or radians. The circumference of a complete circle. The word circumference simply means the length of the entire perimeter. So find the center of the circle and establish the radius length. And we've already discussed earlier that the circumference can be found by taking the radius length and wrapping it around the circle, and it would take 2 pi radii to wrap around the entire circle. Or if you want to put this in terms of diameter, if you know the diameter of the circle, then you simply have to do pi copies of the diameter to wrap around the entire circle. And it's simple to see that 2 times r is simply this d for diameter. Now if you have an incomplete circular arc, so how long is this blue curve? Let's call this L for length of the arc, and we use C for the entire circumference. We will be able to figure this out by determining what the subtended angle is here. If this angle is alpha degrees, then we simply have to figure out what fraction of the entire circle is alpha degrees. So we say alpha degrees divided by 360 degrees, just like we did before. And this will give me the fraction of the entire circle we're looking at for this arc. So we multiply that fraction by the entire circumference. So 2 pi r, or you can put pi d. Now if this angle is measured in beta radians, then similarly we would say the length of the arc is take beta radians and divide it by 2 pi radians to figure out what fraction of the circle we're looking at, and then multiply that fraction by the entire circumference. In this case, we can simplify. The 2 and the pi both cancel, leaving us simply beta times r. And this concludes our discussion on angles and circles.